So, hello everyone. This is the uh, second part of the linear regression that will be carrying and that will be covering the topic for the multiple linear regression. So, as discussed for the simple linear regression, we are trying to we have two variables and we are trying to form an associative relationship between them. In multiple linear regressions, there will be multiple independent variables, and we'll be seeing the outcome of them, which are the variables which in the data set uh, which affects the outcome, which does not affect the outcome, are the other variables which are contributing to the outcome. Are they uh, related to each other, or so the independent variables being related to each other or not? And which becomes a problem in multiple linear regression as well. The relation of independent variables being with each other. So let's get started with a multiple linear regression. The It's a supervised learning technique for finding the existence of the association relationship between a dependent variable and several independent variables. For the simple linear regression, you can see the mathematical representation of it. But for a multiple, which is y equals to beta 0 plus beta 1 xi plus epsilon I, which is for a given data set uh, where the I values go from starts from 1 to n, etc. For multiple linear regression, the y equals to beta 0 plus beta 1 x1i plus beta 2 x2i until beta k x ki plus epsilon I. Epsilon I indicating the errors. The beta I starting from 1 to k, representing the partial regression coefficients. This means that it measures the relationship between the explanatory variable xi and the response variable y, controlling for the effects of all the explanatory variables in the model. So, in other words, the partial regression coefficient beta I answers the question: how does the response variable y change when the explanatory variable xi changes by 1 unit, while all other explanatory variables are held constant? So, like similar to the simple linear regression, we assumed a certain there were certain assumptions under which we worked with, and there are certain assumptions for the multiple linear regression model as well. First is a regression model is a linear in regression parameters. The residual follow a normal distribution, and the expected value of mean of the residual is 0. In time series data, the residuals are assumed to be uncorrelated. The variance of the residuals is constant for all the values of xi. When the variance of the residual is constant, it's called as homoscedasticity. Non-constant variance means heteroscedasticity. There is no high correlation between the independent variable in the model. Multicollinearity can destabilize the model and can result in the correct estimation of the regression parameters. Multicollinearity is something that I was talking about in the intro of the intro of this session. So the partial regression coefficients are estimated by minimizing the sum of squared errors. We will use auction pricing for layers in the IPL dataset. So this is a snapshot of what the what the columns are, what the descriptions mean. Some of them are the age and their categories. You can see the category 1 for age, where player are less than 25 are playing. 2 means the age between 25 to 35, and category 3 means more than age 35. So we start with loading the data set first. So we'll create a data frame and then read the CSV file, and also we'll be printing the. So you can see the info of the data set of the data frame that is being used here. That auto info shows the information about the data frame. So you can see the number of entries, number of columns, what are the data types, and what is the memory usage that that it uses. So displaying the first 5 records of the records that the dataset contains. This is what it looks like. So what are we trying to do here? We are trying to model or make a model which predicts the influence of the player's sold price based on the player's stats and predict the player's auction prices in future. So based on the playing stats of the player, what we are trying to do is we are to how much it influences the selling price of the player, and what would be the predicting what would be the price of the player based on the stats uh, in the future. So we'll be using only the uh, data that we that puts any input into it. So that would be for so also, which also means that we'll be removing some of the columns from our data set. So you can see the serial number and the base price being the example for removing, as they do not contribute to any of the calculations that we'll be making further. Then making the X features, which includes the feature in model building, the categorical variable, so age, country, playing role, captaincy experience cannot be directly included into the regression model, and they must be encoded using dummy variables before incorporating in the model building. So a regression model basically does not take categorical variables, and therefore we'll be creating a dummy model on dummy variables for using them into the model. So first we'll be creating the models, the categorical models, and if a categorical variable has n categories, so we'll be creating the categorical variables, and the variables has n categories, and then we'll need n minus 1 dummy variables. You can see the X features, which contains the age, country, playing role, T runs, T wickets, ODI runs, ODI strike rate of batting, ODI strike rate of bowling, ODI wickets, etc. So as we discussed that regression models do not take categorical values, you can see the how we have created the dummy variables. First, we'll be using dot unique method for the variables, and then having them create dummy variables. So you can see the screenshot where the all-rounder, batsman, bowler, and wicketkeeper, they are given a random values for it. And now this is for the creating the dummy variables for the rest of the features which contains the categorical variables. So remember the categories that we took. Now we are incorporating it for the all the categorical values that are in the data frame, and that are in the data frame. So after creating new dummy variables, we'll refer back to the X feature that we created at the start here again. So now splitting the data set into the train and validation set. So so remember that random state that sorry, for the so we will be splitting the data set into 80 and 20 for training and testing respectively. But what if we want to keep the same records that go into the training and testing set remain same and the results can be reproduced? So the random state, giving it a numerical value, will make sure that the records that go into the training set and the test set remain unchanged, and hence the results can be reproduced whenever we use that random state's numerical value. So here 0, 1 and 42 are some of the common numbers that are used, which are randomly chosen and commonly used. So the changing the random seed to another number will give you another split set of training and test data set. So you can see the darkened line for the darkened points for the Python commands in order to create it. The X values for the IPL auction encoded DF that we created, the Y value for the sold price as we are trying to predict the sold price of the player, and what influenced the sold price, what player stats influences the sold price, the train test split being used, which is for the 80-20, and the random state numerical value is given as 42. Now building the model on the training data set, we build and analyze the model summary. So this is, you can see the Jupyter Notebooks screenshot here. We are summarizing the IPL model 1 over here, and you can see the summary, the R squared value, which is 0.554, the coefficient standard error, the p value, and etc. So as we are dealing with multiple independent variables, there can exist a multi-collinearity, which is nothing but the relation of independent variables being affected on each other. So how we can solve that issue in order to get a more stable and a model which works in an intended manner. So starting with the effect of multicollinearity on the model. So the standard error of estimate, which is SE beta head, is inflated. The statistically significant explanatory variable may be labeled as statistically insignificant due to the large p-value. This is because when the standard error of the estimate is inflated, it results in an underestimation of the t-statistic value. The sign of the regression coefficient may be different. That is, instead of negative value of a regression coefficient, we may have a positive regression coefficient and vice versa. Then adding and removing a variable or even an observation may result in large variation in regression coefficient estimates. The variance inflation factor VIF is used in order to solve multicollinearity. So we'll be using the VIF, which is a measure used for identifying an existence of the multicollinearity. It identifies a correlation between the independent variables and the strength of that correlation. The for an independent variable x1 and x2 and their regression between them, and r1 to be the r squared value of this model. So for the model, uh, x1 equals to alpha 0 plus alpha 1 x2. The variance inflation factor mathematically can be represented as VIF equals to 1 by 1 minus R12 square, where R12 is nothing but the R squared value of the model. The VIF values can be interpreted as uh, uh, let's see how the interpretation of the VIF values happens. So it starts with 1 and has no upper limit, but the value of 1 indicates that there is no correlation between the independent variables and any other. The VIFs between 1 and 4 suggest that the moderate correlation, but not severe enough to warrant corrective measures. Then greater than 4 represents the critical levels of multicollinearity, where the coefficients are poorly estimated and the p-values are questionable. So the square root of VIF is the value by which the t-statistic value is deflated. So the VIF value of greater than 4 requires further investigation to assess the impact of the multicollinearity. One approach to eliminate the multicollinearity is to remove one of the variables from the model building. So you can see the variance inflation factor method will be used from the stats models package. To be precise, stats model, stats outliers influence package. So for getting the VIF factors or the variance inflation factors, we'll use the X matrix and give them the we'll first define VIF for the X matrix and I for looping through the range of the matrix. Then putting the VIF factors columns and the VIF and returning the VIF factors. Sorry. Then passing the VIF factors, get VIF factors and giving them the X features for it and printing the values of VIF factors. Now checking the correlation of the columns with the large VIFs. The for VIF factors greater than 4, the and we so basically what okay okay, sorry. So you can see the column and the VIF values on the right side of the screen, and how much their values correspond. So strike rate of bowling, average bowling are some of the values which are which have really high VIF values. And if we plot these VIF values on a heat map using the C bond. You can see the correlations of different uh, variables on each other. So T runs and ODI runs S are highly correlated, whereas ODI wickets and T wickets are highly correlated, and you can see their values over there. The batsman features like runs, average sixers are highly correlated, while bowlers stats of average economy and the strike rate of bowling are highly correlated. So the potential solution include the following: remove some of the highly correlated independent variables, linearly combine the independent variables, such as adding them together. Partial least squares regression uses principal component analysis to create a set of uncorrelated components to include in the model. Then lasso and ridge regression are advanced forms of regression analysis that can handle multicollinearity. If you know how to perform linear list squares regression, you will be able to handle these analyses with just a little additional study. So to avoid multicollinearity, depending on the domain knowledge and data, we can keep only one column from each group of highly correlated variables and remove the others, which can be achieved by going through multiple iterations and deciding the final set of variables uh, which do not have any multicollinearity or does not affect much. So these values will out of them will be dropping one of them, uh, dropping one of them, uh, and deciding for ourselves. So the columns that we decided to remove were T runs, T wickets, runs, HS, average runs, average bowling, economy, etc. Till a strike rate of bowling. Then giving X new features being created and uh, removing uh, the columns to be removed that we just created from the X features that we used before, and getting the VIF factors for the X new features that we just created for the removed columns that we didn't want. And you can see now that the scores that were present before are no longer there, and the values are somewhat in a manageable range. You can see the scores over here for reference and over here. So building a new model after removing the collinearity, so which will say IPL model 2 and the summary of it. So when you summarize this, you can see the data the data it outputs in a way, or summarizes the summary it gives. So based on the p-values on only the variable country India, country England, Sixers, and captaincy experience have come out statistically significant. So the features that decide the sold price are whether the players belong to India or England, that is origin country or the of the player, how many sixes has the player hit in previous versions of the IPL, how many wickets have been taken, and whether the player has any previous captaincy experience or not. And for the selected columns, we have created a significant variables, and then when we summarize this is the output that we get. So inference from the model, all the variables are statistically significant and the p-value is less than 0.05. All the overall model is significant with an F statistic p-value less than 0.05, and the model explains 71.5% of the variance in sold price, and an R squared value of 0.715 and an adjusted squared R squared for 0.704. You can see the adjusted R squared and the R squared on the topmost last entry for R squared, and on the right the adjusted R squared value. So plotting these the residuals of the multiple linear regression, for the test of normality of residuals, one of the important assumptions that the regression is that the residuals should not normally distributed, be normally distributed. Sorry. One of the important assumptions the regression is that residuals should be normally distributed. And when we plot the graphs for the given code, you can see that the points are almost in the approximation of the line. So the residual plot for homoscedasticity and a model specification. The residual plot is a plot between the standardized fitted values and residuals. So it should not form any shape. Funnel shape indicates the presence of heteroscedasticity. Then any pattern in the residual plot may also indicate the use of incorrect functional form in the regression model development. For the plot, you can see that for plotting the values of the residuals, we are not getting any shape or any funnel shape for indicating the absence of the heteroscedasticity. Then detecting the influencers. So in OLS estimate, or the ordinary least squares estimate, we assume that each record in the data has equal influence on the model parameters, which may not be true. And the leverage values of more than 3k plus 1 by n are treated as highly influential observations, where k is the number of variables and n is the number of observations. So you can see for train X shape 1 and n for train X shape 0, we are printing the number of we are printing the value of k and the value of n, and you can see the 4 and 104 for the value of k and n respectively. Then the leverage cutoff, which is of 0.144. Now detecting the influences with the help of the plots, you can see the size of the circles as well as them being very away from the normal plots. The 23, 83 and 58 are somewhere uh, appearing different from the normal plots. So they are comparatively high leverage with residuals. Now filtering out the influential observations. So we'll get this output. So we don't have large residuals, so may not be required to remove, but if needed, we can use the drop method in order to do so. So the 23, 58 and 83 are these entries, and you can see their residual values and stuff. So transforming a response variable, transformation is a process of deriving new dependent or independent variables to identify the correct functional form of the regression model. So the functional relationship or the functional form that we said for linear multiple linear regression was in terms of y, xi, x and x y, xi, x2, etc. But these functional forms can will be changed for the response variable. So you can see that a y being replaced with a log y or 1 by y, and similar thing happening for the x values as well, which is for log x. You can have instead of x, it can be log x, 1 by x, etc. So the transformation of MLR is used to address the following issues, which is poor fit, pattern in residual analysis indicating a potential non-linear relationship between the dependent and the independent variables. Residuals do not follow a normal distribution. Residuals are not homoscedastic, which is they are not constant variance. So the new response variable is taken by square root of the existing values. So using the NumPy square root method, we'll get those values and have the summary of the model 4. So you can see the R squared value being equal to 0.75 in the summary, just in the same column as number of observations in the second part of the image. So for plotting the probability plot for regression standardized residuals, you can see that it is following a normal distribution by approximately being around the line. So making the predictions on the validation set, the model predicts square root of the sold price. We need to square the predicted values to get the actual sold price of the players, where will be so we'll be using the NumPy power method for that, and measuring the root mean squared on the validation set. We are getting the output for the NP square root for the PRED y and the test y values, which is 496,151.181. Then the measuring the R squared values on the end with the help of NP round, and passing the R2 square, the parameters of PRED y, test y to, and getting the value of 0.44. So the accuracy on validation set is 0.44. The accuracy on the training set is 0.75. So you can see the accuracy of on the training set is more than the accuracy on the validation set, which can indicate the sign of overfitting. Now this is an and this is a part taken from for the autocorrelation. So between the error terms of one of the assumptions of the regression model is that there should be no correlation between error terms. If there is an autocorrelation, the standard error estimates of the beta coefficient may be underestimated, and that will result in overestimation of the t statistic value, which in turn will result in a low p-value. Thus, a variable which has no statistically significant relationship with the response variable may be accepted in the model due to the presence of the autocorrelation. The presence of the autocorrelation can be established using the Durbin-Watson test that we have been seeing in the summary of the Durbin-Watson test. As you can see on the summary screenshot on the bottom right, we are getting the value of 1.879. 1.879, sorry. So if we make few more changes, we'll get the model summary to have the Durbin-Watson statistic value to 2.2. So if the Durbin-Watson statistic value is 2.2, then the we have concluded that the error terms are not autocorrelated. And also note the autocorrelation is not relevant in the case of the time series data. So these are some of the references used for both the simple linear regression and the multiple linear regressions. So yeah, thanks a lot for listening, and thank you.
Thank you, Jamie. Thank you so much.